Last video we explored the engine room machinery that uses steam to power the SS Badger. But where does all that steam come from? Deep inside the ship are 4 coal stoker boilers, steam-powered draft fans, and conveyors that move coal from the bunkers to the furnaces. Hello, this is Jason from Steam, Electricity, and Propulsion. In this video, we'll explore how the Badger's boiler room works. From moving coal and air, to generating the steam that powers the last coal-fired passenger ship in the US. Then, we'll watch the firemen operate the boilers and see this machinery in action. When the ship is in port, only half the furnaces are lit. Instead of operating all of the grates at a low firing rate, dampers are closed and half of the fire is dumped. This concentrates the airflow through the remaining fire, helping coal burn more efficiently and produce less smoke. Coal is fed into the boilers with modern Detroit stokers. Similar stokers can be found on the abandoned boiler at the North Dakota State Hospital and on the Foster Wheeler boiler at the Hibbing Cogen Steam Plant. The firing rate is controlled by a variable frequency drive which can run the coal feeder at any speed. A second motor drives a rotary beater that scatters the coal evenly across the grate. Variable frequency drives didn't exist in 1953, so how did the stoker originally work? The ship originally had mechanical Firite stokers, which is what the William A. Irvin has. A wedge was used to adjust the amount of slack between an eccentric driven lever and the coal feeder lever with the latch. When more slack was introduced between the two levers, the feeder traveled a shorter distance on each stroke, reducing the amount of coal delivered to the furnace. Modern machinery is often computer controlled, but older equipment could do the exact same thing with moving levers and cranks. Here's the forced draft blower while we're in port. At the top of a passenger stairway, we can hear the steam-powered induced draft blowers whining away. Now that the ship is underway, let's go through this watertight door and explore the boiler room. That machine is a steam-powered railway air compressor, but it no longer operates. We'll take a closer look at the air compressors later. Now we follow Chief Engineer Andrew through another watertight door into the coal bunker room. This compartment contains the coal chutes and conveyors located beneath the bunkers. A fireman uses a shovel to guide coal onto the conveyor. The conveyor carries the coal upward and dumps it through a hatch equipped with a watertight door. The coal bunker room is a tight, confined space. There is only one watertight door leading to the boiler room and no stairway access. For additional safety, an escape ladder leads directly to the car deck. The coal is then delivered to the stoker hoppers, where it is fed into the boilers. This watertight door between the engine room and boiler room can only be operated by hand. It can be left open since this is a manned space. Without combustion air, the coal would not burn. This electric-powered forced draft fan supplies air beneath the grates. A VFD-controlled 20 horsepower motor can operate at speeds up to 1,800 RPM, while the belt drive reduces the fan speed to approximately 1,000 RPM. The smaller fans provide secondary air above the fire, helping burn off gases from the coal and reduce smoke. But forcing air into the furnace is only half of the process. I follow Chief Engineer Andrew up a narrow stairway away from the boiler room. We are about to see some unusual machinery that most people have never encountered. As we walk down the hallway, we can hear the distinctive whine of steam turbines. Inside this room are Terry steam turbines connected by long belts to the induced draft fans. The belts travel upward through the ship and drive large pulleys mounted on the fans. The induced draft fans normally operate between 700 and 1,300 RPM. Although the turbines are capable of producing up to 60 horsepower, the fans typically require only about 30 horsepower during normal operation. The purpose of these fans is to maintain a slight vacuum inside the furnaces. These fans must maintain a negative 0.2 draft in the furnaces to prevent fire and smoke from coming out. Before reaching the fans, the exhaust gases pass through multi-cyclones which remove ash from the flue gas. These devices spin the gas at high speed so centrifugal force throws the heavier ash particles out of the flow stream. Because the fans pull gases through the boilers and cyclones, they produce much higher suction pressure than the furnace itself. Under normal loads, the fans produce about -3 inches of draft. At 60 horsepower and 1,300 RPM, these fans can pull up to -8 inches of draft. As steam demand changes, a pneumatic throttle valve automatically adjusts the steam flow to the turbines, changing fan speed as required. The turbine exhaust steam is then routed to the deaerator to preheat feed water. Listen carefully. The turbines are speeding up. Chief Engineer Andrew told me this happened because the firemen were raking the fires. I asked the ship's engineers about this, but it's not clear how this affects the fans. While most passengers never see this machinery, they will hear it. The turbine-driven draft fans produce a distinctive whine that can be heard in nearby stairwells. Deep down in the boiler room, we see a fireman throwing coal into the fire. Next, he would rake the fire to restart it. This is one of the most important jobs in the boiler room. It's hard work, but it's necessary so the boilers don't get clogged with ash. First, the stoker is shut off to let the coal burn out on one side of the grate. Then, the damper is closed. Some firemen like to rake the hot coals forward, but this step is not necessary. Once the fireman raked the coal and ash forward, he pulls the dump grate lever to release the ash to the pit under the grate. Let's let the fireman explain why raking ash is important before coming into port.
I gotta have all these pits flung over and pulled by 6:15. So when we shut this off and come into port, we have plenty of power to be able to maneuver. Otherwise we don't. We won't have the power. We won't have the air.
Chief Andrew will simply dump the fire without raking it forward. Here we see how the 3 sections of the grate turns to dump ash. Now we need to restart the fire to regain steam capacity. A fireman will rake hot coal over from the other grate and spread it across the empty grate. The stoker will spread fresh coal over it and rebuild the fire. Lastly, the fireman will use a long hoe to pull the ash out of the pit and push it into a collector. After watching the crew do this job and listening to their advice, I got to try it myself. I first got to rake ash, but what I'm showing was not my first time. The dump grates were large and heavy, and I initially struggled to operate them. Later, I was able to rake the ash from beneath the boilers. This footage was recorded during my final day aboard the ship after arriving in Wisconsin. By then, I had gained some experience, but moving ash with the heavy hoe was still a real workout. I also got the opportunity to wing the fire over, which is the final step of the process. Working with a live coal fire aboard a steamship was a very unique experience. Besides ash buildup in the furnaces, soot can also accumulate on the boiler tubes. To remove the soot, we operate these soot blowers. When the chains are pulled, a system of gears rotates a pipe fitted with steam nozzles. Steam is then directed along the boiler tubes, blowing the soot loose. A cam mounted on the large gear operates a poppet valve which admits steam to the soot blower as it rotates. At the top of the boiler room are the steam drums and feed water regulators. As steam demand changes, the water level inside the boilers can fluctuate. These valves use pneumatic actuators to automatically control the flow of water into the boilers. The feed water pumps maintain a pressure slightly higher than boiler pressure. Each of the 3 coffin pumps is rated for 200 gallons per minute at 500 psi. Before entering the boilers, the water passes through economizers which capture waste heat from the exhaust gases. Each Foster Wheeler D-type boiler can produce up to 30,000 pounds of steam per hour. Even at full speed ahead, the Badger's engines only need about 2,500 horsepower each. Together, both engines consume roughly 45,000 pounds of steam per hour, meaning the boilers are operating at only about 50% of their maximum capacity during normal service. Lots of machinery in the boiler room and engine room uses compressed air. The ship has twin 15 horsepower electric air compressors which can produce approximately 170 psi air for storage. Many ships of this era already had electric air compressors. The Badger's modern electric compressors take advantage of the ship's powerful generators and are more efficient than the old steam locomotive air compressors they replaced. The Badger's boilers aren't just large steel pressure vessels. Keeping them operating requires coal stokers, draft fans, feed water pumps, and soot blowers. I'd like to thank retired Chief Engineer Kevin for explaining Firite stokers to me, and Junior Chief Robert for helping with my tour. From the turbine-powered draft fans to the coal stokers, most of this type of machinery has disappeared from the modern world. This would all be gone if it weren't for all the people who buy tickets to ride this ship across Lake Michigan. I got to experience working on the last remaining stoker-fired marine boilers in the world. It was an experience I will never forget. In another Badger video, we will see the process of how the ship is maneuvered in port from inside the engine room. If you'd like to learn more about coal-fired steam systems, check out this video about a coal boiler equipped with Zern stokers.